Vector displacement is one of those methods that you hear about. You hear about it being complicated, you see it in November stuff, and really, there are a couple, but generally there are no good resources for very, very beginner vector displacement. I just want to focus on some simple vector displacement, taking a cube and turning it into a pyramid, a sphere, a cylinder, a cone, basically swapping out primitives with genus 0, if you know about that topological thing about shapes. Point is, we're going to be taking shapes and converting them into each other, because I don't think there is an easier way to teach vector displacement. So get your Blender open and ready, because by the end of this tutorial, you are going to know what it means for displacement to be vector displacement specifically and how to do it. So let's do that. A couple things to keep in mind whenever you're doing vector displacement. You need a couple settings before you can even do it in the first place, which, inherently confusing, but fuck it, that's just the case. First of all, render engine, it needs to be set to cycles. Deformation or just in, general material-based displacement does not work unless you're in cycles. You could do the displacement modifier, and it works with Eevee, but first of all, make sure you are in cycles. That's the first thing. Second thing to think about is, since we are doing displacement, deformation of the actual geometry, like we're moving around vertices, it's always useful for a modifier to be added. Which one is that? That's going to be subdivision surface. I'm just going to set this to simple so that it doesn't actually change our geometry, and we're just going to add a couple divisions. So what's happening here, and we can actually view this with a wireframe shader, is we're adding additional geometry even though the silhouette looks identical. So again, it's always useful for whatever base mesh you're starting off with to have additional geometry. And then the final thing, and this is where I think a lot of people probably get caught up thinking, damn, I was never cut out for this, is in the material settings. Make sure you scroll all the way down and go to the settings inside of the material settings, kind of like those Russian dolls. And in displacement, change this from bump only to either displacement only or displacement and bump. In other words, we want our displacement not to just be based on normal mapping and all that bump mapping stuff, but also geometry-based displacement. I use displacement only because the third option has some lighting artifacts and stuff like that. I think it's because it's trying to preserve some kind of orientation of normals or something like that. Point is, use displacement only. So once you have the render engine set to cycles, the subdivision surface, and the material settings with displacement only, you are now ready to begin. So vector displacement, how do you do it? What is it? And is it important for what it means to be a human? Long story short, everything we do in the material, the material workspace, what's this called? Shading workspace, shader editor. Everything we do in here kind of goes into three categories. It's either a surface property, like the principled VSDF, where we're literally changing what's on the surface. It's either that, a volume property, so in other words, kind of like a volumetric, cloud, smoke, stuff like that, so the interior of the mesh. And finally, we have the displacement type, which is the one we care about, and this is about changing the geometry to begin with. So we are not concerned with either of these green sockets. We are just going to be manipulating this displacement socket, okay? And really, you can just plug in a vector to begin with, and we'll talk about what that means. So for example, I'm going to use combine x, y, z. This is just a 3-component vector, x, y, and z. So again, it's kind of like a vector in 3-dimensional space with an x, y, and z component. You connect this, and if it actually lets you do that, you're going to see that nothing is happening. Why? Because in some sense, we are moving our geometry by the 0, 0, 0 vector. In other words, do nothing is what Blender has right now. Instead of this, what we can do is say move it on the x-axis, and it's going to do that by exactly 2 units, 3 units, whatever it may be. We can also go down the y-axis and the z-axis, okay? And so far, it's pretty simple, but there's kind of a key insight here that's not so obvious. The key insight is that this vector describes some kind of transformation. It does, but it doesn't describe the final position of the vertices, right? It's not like every one of these 8 vertices moves to the vector 3, 0, 0. It's that everything's being displaced. It's being changed by this vector. So in other words, we are adding the vector 3, 0, 0, 0, which basically says move every vertex 3 units to the right, okay? So again, key insight here is we're not messing with the texture coordinates and all that. We're just saying displace, not final transformation, just move it, okay? And you could also do this with a single value, although I think it will assume that x, y, and z are the same in this case. So we'll be moving diagonally. So right now it's saying -2.2 for x, y, and z, etc. And that's a thing. So we could just say, displace it in one direction, but that's not too interesting because we want to like reshape the thing, meaning we kind of need information about this geometry to begin with. Because, you could do the combine X, Y, Z for an arbitrary mesh like the Suzanne monkey or a sphere or anything like that, but it doesn't really say anything about what mesh this is. So to do that, moving on, we need texture coordinates. And you've probably already messed with texture coordinates. We have generated, normal, UV, blah, 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 blah. Long story short, object coordinates are usually the easiest to work with because they basically tell us exactly what the position of every like point or vector on this cube is. So for example, you're going to see that it's almost as if you can imagine that there's like an origin at the middle. That's why there's these crosses. That would be the vector 0, 0, 0. As we go up, everything tends to get a bit bluer because the z component's getting larger, and we can actually like view it like this. So we can see the x component getting larger as it gets brighter and whiter. Same with the y-axis and the z-axis, and this just gives us the points, the vectors of every position on this cube. Okay, so ideally we like to use object coordinates or kind of identically position coordinates from the geometry node. The only difference here is if you move the cube, it doesn't move with it. Whereas object coordinates do, because they're based on the origin of the object, okay? So we're going to be using object coordinates on a very technical level. If you're actually putting textures and masks and stuff on here, and you want them to move with the deformation, we actually need to use generated coordinates and transform those, but for now, do not worry about that. For now, we're just kind of having this white mesh that we're going to be manipulating using object coordinates, okay? So first transformation we want to do is be able to turn this cube into, let's say, a pyramid. And you might be thinking, okay, how do we do that without hopping into edit mode, taking this face and like scaling it down? Well, in some sense, this instruction of scaling down the top face is exactly what we're going to do in vector displacement, right? So as we go up the z-axis, what we want is for x and y, the other two axes, to be pinched so that at the top they're at a scale of 0, okay? So how do we kind of describe that? Well, first of all, we separate by x, y, z. So I can say, okay, we want to look at the z component as we're going up. Again, we're baking these edit mode instructions into like a mathematical procedural kind of instruction manual. Okay, we're saying we want the z component. One kind of technicality is right now, z is -1 over here, then it's 0, then it's 1, because again, half this cube is under the ground plane. Before we do any transformation, I just want to fix that. So map range -1 to 1 is basically going to say take the input -1 to 1 and map it to 0 to 1. So now, instead of going from -1 to 0 to 1, starts at 0. So wherever we have -1, map it to 0. And then go all the way up to 1. And in fact, I guess we want to invert this, so I'm just going to switch these around, okay? So right now what we have is a z direction gradient that is 1 on the bottom and 0 on the top, which is perfect because what we want to do is scale this as it goes up, right? So here it should be scaled by 0, so it's pinched, and here it should be preserved. So we're scaling or multiplying by 1. And just before we actually do this transformation, just so you can see what's happening, what we're going to do is we're going to do some kind of transformation with object coordinates. And if we were to plug this into displacement directly, you're going to see that, I mean, we could have it like move around like we did before. But one thing you're noticing is that the cube itself got bigger. Again, why is this the case? Because displacement is a change. It's not a final position. So in some sense, we've actually added in object coordinates that we don't even want. So no matter what we do, at the very last step of your vector displacement should always be subtracting away the original coordinate system. Again, we need to get rid of the initial state. So now we have a setup that lets us kind of add this. So this is identical to doing that combine x, y, z from before, but now we're just adding object coordinates and then subtracting them again. The reason to do this is because we need to transform those object coordinates in the first place. Otherwise, we wouldn't be messing with adding and subtracting the same thing. Doesn't really make sense, right? And, we don't have to have addition. We could have it be multiply. So let's set this to 1 so nothing changes. You could scale on each axis individually, and that's pretty much what we're going to be doing just with a gradient, okay? So that's the lesson. So again, we want to be using this gradient. As we go up the z-axis, we want to scale x and y by this gradient. So again, I guess I shouldn't have deleted it. What we're going to be doing is using a multiply. Set this to 1, 1, 1 so nothing changes. And I just want to be very, very clear about this. Let me actually clean this up so it's easier to look at. I want to be very clear about this. The last step of the displacement, of the vector displacement, should always be subtracting the initial coordinate system, whichever one you used, whether it be a UV or a modified generated coordinates like I was talking about. A bit too advanced for this one. or object coordinates or whatever, you always end over here by subtracting that same coordinate system. So I usually like to give this thing a color to remember. We could do a bunch of stuff here, but it has to connect to the subtraction at the very end. Okay, so how do we turn this into a pyramid, for example? Well, we could multiply not by like a single vector like 1, 1, 1, but we can use the gradient. So I'm just going to connect this here for a bit more control. 1, 1, 1 is basically the same thing we had before, but this time for the x and y axis, I'm going to use this gradient. So I'm just going to connect it here and here. And you can see it gives us a very nice pyramid that gives us, the BSDF surface once we actually look at it, okay? So this is our transformation. Again, the reason it works is we have the z component isolated. Let's not have this transformation. We have the z component isolated. As we go up, the x and y, since that's what we have connected, are going to be scaled closer and closer to 0. In other words, that's the same thing as like scaling that face in. Okay, so let's apply that. And one kind of cool thing is once you have this kind of mini node group, or I guess it's not a node group, this mini setup, you can take it, Control G, and turn it into a node group. And I guess we don't need to actually see the result, so let me just get rid of that. We don't actually need to see the gradient. Just have the vector displacement. The neat thing about this is we've basically made a step that describes exactly, if I can remember how to spell pyramid. Need to watch more Yu-Gi-Oh! Exactly how to make a pyramid, which means we can actually take these, we could blend them together with like a mix node or something like that. And I guess make sure that you're blending in the original coordinate system. It will like to take generated for some reason. We can mix these together so we can actually have a transformation effect going from one to the other, okay? So that's one. Let's say now we want to turn this cube, so not really the pyramid, but the cube. And by the way, just to be very clear about what's going on here, again, we are deforming the actual geometry. So you can see right now we have the subdivided cube that we can have a arbitrary number of subdivisions. We take this, we do our vector displacement, and when we mix it, you can see it's actually moving the actual geometry, which is why the wireframe's changing. And the more geometry we have for this, typically the better. For a pyramid, it doesn't matter because it even works with as few as 8 vertices. But for a sphere, it does matter. So let's say we want to take this cube and turn it into a sphere. With the pyramid, we had an easy trick of pinching it near the top, but how would we do like a similar thing? How would we mathematically describe turning this cube into a sphere? Well, if you were to model it, I'd probably subdivide it a couple times just to add some geometry, and then there's this like toSphere command that I think should let us, make it into a sphere. So if we were doing it in edit mode, this would probably be the technique. So how do we take this and turn it into vector displacement mathematical knowledge? Language, that's probably it. So for the divisions, we already have it taken care of, but how do we do the toSphere command? Well, the way the toSphere command works is what it does is it takes all our points, I guess every vertex we have depending on the number of subdivisions. It looks at the length, or in other words, the magnitude of that position vector. So again, it's looking at all the points, it's looking at how far away it is from the origin, and then it's saying we want to normalize those lengths. So every length should be 1 or 2 or whatever. And the reason that works is because a sphere is basically a set of points that are equidistant from an origin. So if we were to make all these points the same distance from the middle, it will kind of map it to a sphere. So the corners are going to be pinched in more. The stuff near the top won't move as much, or towards the middle won't move as much, etc. Okay? So in vector math language, we do this by taking, again, even though we have this mix, we can take this as our last step of the vector displacement, so we can chain more stuff here. What we could do is add in a vector math node, put that in here, and there's a command exactly for this, normalize. And again, what it does is it looks at all the lengths of these incoming vectors, and it multiplies, or it scales them by the reciprocal. In other words, it normalizes them, takes them all to the same length. And this is a good time where you could do shade smooth to make it look a bit nicer. And just like last time, we could mix these two steps together. So now we're going from a cube to a sphere. And by the way, if you want shade smooth without like smoothing on the cube version, one thing you could do is in the normals, apply auto smooth, which is saying only smooth if the angle between any two polygons or faces is like less than some threshold 30 degrees, although sometimes we need to bump it a bit more. And another way to make this better without doing that is you could add in more geometry so there's a harsher crease. But now we have a way to go from like a sphere to a cube and to a pyramid, and you can even go from a pyramid to a sphere, although it won't work as well because the geometry has actually been manipulated. So we're kind of pulling geometry from weird places, especially near the top, where we've basically compressed the entire top face. So order of operations does in fact matter. But now we have a way to turn this into a sphere. Let's do one or two more. Let's do a cylinder. If I was to turn this sphere, so again, you could start with the cube, the pyramid, or whatever, but since we're doing them one after another, how would I turn the sphere into a cylinder? Well, if I was to take this and kind of like stretch it out like this, so you have to imagine the sphere stretching with this, if we were to stretch it out and flatten off the top and bottom, that would give us exactly that. How do we describe this mathematically? This one's actually pretty simple. We just separate by x, y, z, so I can look at, again, the x, y, or z. So x, we have to be over here to see it. What we want to say is take the top hemisphere, so again, where z values are positive. We want to like map it so they're kind of like stretched up to the top so they make a flat circle, kind of like you were taking an eggshell and just flattening it, or like one of those hopping toys, if you know what I'm talking about. We want to do that, and then for the bottom hemisphere, we want to do the opposite. In other words, where we have a positive z value, map it to 1, negative z value, map it to -1. And there's actually a math function for that. It's called sine. In other words, does it have a plus or minus next to it? So not like sine in trigonometry, but sine like this. And this will map all positive values to 1 and negative values to -1. In other words, we've now manipulated our z coordinate, and we don't really want to manipulate x or y. Those are fine. We just want to do some z stretching, okay? So now if we were to take our x and just put it here, our y here, and our modified z here, you're going to see that it gives us a new kind of map that we could connect. Again, whatever you do, last step should always be going to the subtraction of the vector displacement. Now it's going to give us a cylinder. Again, what's happening here, and this would be easier to see once we mix everything together, I suppose. So again, let's mix now the, what is this? This is the sphere now. Let's mix the sphere with the cylinder. You can see what's happening is the x and y coordinates are staying the same, but we're just kind of stretching it like this. And you're seeing that there's some like geometry issues. These things get better the more geometry you have. So we could actually just add more divisions, and you can see it cleans it up a bit. And I think part of the issue here is we started off with like a pyramid or something. Or is it the auto smooth? Did we still have that enabled? Point is, the more geometry you have for this, the better. So let's go one step at a time just to see what we have so far. Again, a lot of these lighting artifacts do go away once you have more geometry. Okay, so let's see what we have so far. So far, is it not updating for some reason? Hold up, we can just fix that very quickly. Why is it doing the cylinder? It's doing the cylinder because I guess it's taking this chain. So I guess we can just plug it in manually. So we started off with a cube. We then made it into a pyramid. And we could actually control that with the mix. I just want to be very clear about each step here. So we have that. Next thing we could do is normalize it. This is what turns it into a sphere, again, normalizing all those lengths. So now we have a sphere. Then we did a conversion using the sine, not trigonometry, but, you know, positive and negative version. We took this, and now we have a cylinder. And by the way, a quick way to fix this shading thing if you don't want to add a bunch of geometry is you could always go back to shade flat. And in fact, now this makes it much smoother. The more geometry you have, the cleaner this will be. So here you can see it's not very. We cleaned this up. Now we have a cylinder, and then if we were to view this mix, this should be the transition between a cylinder and a sphere. Okay, final shape now, and I guess we'll keep it on shade flat. Shade smooth is kind of perfect if you have a spherical shape, but otherwise, I guess it's not too hot of a commodity, you know. So final step, how do we turn this into a cone? Well, if you think about it, the way you make this into a cone is the same thing as last time. We'd kind of want to pinch the top of this, just like last time. So instead of taking a cube to a pyramid, now it's a cylinder to a cone. And because that transformation's the same, again, we want the z-axis, make that gradient, and pinch x and y, we could actually take the very same node group as before, and this is where the procedural approach is very powerful, because you could literally just take this, copy and paste it, and now you have a cone, right? Because again, it's the same idea. We're just pinching as we go up on the z gradient. So we can even add a mix for that, so you can see what that is doing. Okay, so now let's kind of look through our whole animation. And by the way, you could combine these to make custom shapes. I didn't even realize we could make a teardrop so easily, but I guess it's true. Let's see, what are we trying to mix here? I think I messed up my like mixing order a little, so that our mix shaders aren't working perfectly. But again, what do we have? Let's go one by one. We have a pyramid that came from a cube. So if we minimize this, cube, pyramid, and then we can mix those. We also have the sphere version. We then also have the cylinder version, which again we could mix, and then finally using the same pyramid node group, which I guess we should just call like a pincher, because it's not very specific to pyramids, just any shape that's pinched. We do that to get the cone. And that's kind of like the essence of a vector displacement. Now, one thing you're probably going to notice if you try to now mess with like surface properties after all this is that whatever kind of like noise texture or whatever we use, so let's say we use a noise texture here, you see that there's a lot of stretching. So like the first solution is you take the last thing before your vector displacement. So these are the modified coordinates. Use this as a vector. It kind of helps, but not really. You're going to notice that with these deformations, it's not really behaving the way you expect to. It doesn't kind of move with the geometry. Like color just kind of appears at the top out of nowhere and stuff like that. And this is the idea of generated coordinates I was talking about before. Generally, object coordinates are the nice one to work with, but generated coordinates are the only, other than UV, are the only coordinate system that kind of move with the deformation. So if we want a texture to stick onto what we're doing, we need to be using generated coordinates. So just a quick trick of how to manipulate these. You take your generated coordinates, you add -0.5, because before it uses the coordinate system of the bounding box. I guess I could show you what that means. So if we were to, I guess, look at this vector displacement step right here and minimize it or mute it, you can see that what we've done is we've transformed these generated coordinates. So before they were off to the corner, now they are centered. Whoops. Now they are centered just like object coordinates. And then finally you take this, you scale it by 2, just so it's the same magnitude. So now everything's going from 0 to 1. And now these should be indistinguishable from object coordinates. So object coordinates and then manipulated generated coordinates. So what you could actually do is use this as your coordinate system. And we could actually take this, turn it into a node group or whatever you want to do. And then again, we want to do the same thing for this subtraction, because you want to subtract away whatever coordinate system you started with. And now we should get some mapping that moves with this. And it's important to think about what step of the displacement you want to use as your texture coordinates. And you could play with that. But now you can see, even though there's the seam down the middle and you can like work with that, you can see now this is kind of moving with it slightly more. In fact, we could just use the original generated coordinates here. And of course, there's going to be stretching vertically because we use that sine function. But if we start off from the beginning, and I know this node graph's starting to look like a mess, but that is welcome to vector displacement. Now you can see, actually, let me go one step further. Now you can see that we started off with a cube, so now we have this noise mapped with these modified generated coordinates, nothing special. But with the pyramid, you can see it's actually moving with the geometry. Other coordinate systems wouldn't do that, so that's kind of special. And then also, it works with every other step, and maybe it will be more clear with the sphere. With the sphere, you can see that, again, everything's moving with it, so that's pretty nice. But yeah. That's kind of like the essence of a vector displacement, moving shapes to other shapes, how to stick a texture, and more importantly, how to think about like mathematical transformations, not doing it in edit mode explicitly, but doing it in this procedural modeling kind of thought process, which is important because soon Blender is going to be getting geometry nodes, which is kind of a system like this, but we're not doing it in fucking materials, right? We're doing it in a way that makes sense. So, hope you enjoyed the tutorial. Hope it was useful. Hope you can now do vector displacement. Chances are maybe none of you could in the beginning, and now maybe 1% of you can. Just play around with it. Download other people's blend files and node groups and see how they generated the vector displacement. For example, that teardrop from before, it's kind of complicated or confusing how you would make that shape, but if you just combine the idea of a cylinder and a cone, apparently it makes it, or a cylinder and a sphere or something. So there's always new things to learn, and yeah, that's pretty much it. See ya.